In this video, we're going to compute the kernel and the image of a linear map between two column spaces defined by multiplication by a matrix. Before I do that, I need to remind you of the rank nullity theorem, which we proved last time. So here is the statement. If you have a linear map T from a vector space V to a vector space W, then the dimension of the image of T, which is called the rank of T, plus the dimension of the kernel of T, which is called the nullity, is equal to the dimension of V, the domain of our linear map T. So you'll recall that if we have a M by N matrix whose entries come from a field F, then we use T subscript A to refer to the linear map from the space of height n column vectors with entries from F to the space of height m column vectors with entries from F, given by T sub A of a vector x is just A multiplied into x. That's what this notation always means. And in this case, the kernel of TA that is the set of all vectors in f to the n which get mapped to the zero vector in f to the m. So you can think of the kernel of TA as the solution space for the matrix equation A times x equals 0. It's the set of all solutions to that matrix equation. That's good because you already know how to compute sets of solutions for systems of linear equations in matrix form. Namely, you can do it using our row-reduced echelon form method. So computing kernels for linear maps of the form T subscript A is something we already know how to do because we already know how to find solutions to systems of linear equations in matrix forms. So let's look at an example of doing this. We will take A to be the matrix 1, 2, 3, 4, 5, 6, 7, 8, 9. I will think of that as a matrix whose entries are real numbers. We're going to try and find the kernel of the linear map TA from R cubed to R cubed. So what we have to do is solve the matrix equation A times a vector equals 0. The row-reduced echelon form method is to form the augmented matrix. So here is that augmented matrix. I've included the final column of zeros, but actually it's a waste of time for me to include that because when we do any row operations to this matrix, the final column will just stay as 0, 0, 0 always. So there's not really any point writing it down, but if I want to write down the actual augmented matrix, that's what it is. And then the row-reduced echelon form method for solving these equations is to do row operations to this until we reach a matrix in row-reduced echelon form. So let's just say if I do some row operations, well, you should pause the video and do it, or you should remember the time when we did this calculation before. In any event, when you do it, what you will get is this: 1, 0, minus 1, 0, 0, 1, 2, 0, 0, 0, 0, 0. And you should remember the method of reading off solutions to a system of linear equations in matrix form. If you don't, go and look it up. So let's give names to the variables which we're working with. Let's say the first column, second column, and third column correspond to variables with the names x, y, and z. Then only the column of the variable z does not contain a leading entry. Therefore, the solutions are obtained by letting z be anything you like, and then x and y will be uniquely determined in terms of z. So the solutions are that you can choose the third variable to be anything you like, and then the first equation corresponding to the first row of that row-reduced echelon form matrix says x equals z. So I would have my z, which I chose freely. X equals z is the equation corresponding to the first row of the row-reduced echelon form matrix, and the second one says y equals minus 2z. So every solution to the matrix equation a times vector x equals 0 is of this form. And we could rewrite that as z times 1 minus 2, 1, if we liked. And what this is then saying is every element of the kernel of TA equals a scalar multiple of the vector 1, 2, minus 1. 1 minus 2, 1. So we could describe the kernel of TA as being the span of the vector, just a single vector, 1 minus 2, 1. Alright, so it is a one-dimensional vector space. It has a single element, 1 minus 2, 1, which spans it, so the vector 1 minus 2, 1 would be a basis for the kernel. Because we know the rank nullity theorem, we can now say what the dimension of the image of TA must be. So rank nullity tells you the dimension of the kernel plus the dimension of the image is equal to the dimension of the domain of A. The dimension of the domain of A is 3 because the dimension of the domain of TA. The dimension of the domain of TA is 3 because the domain of TA is r cubed. So rank nullity would now tell us that the dimension of the image plus the dimension of the kernel, which we know to be 1, will be equal to the dimension of the domain of TA, which is the dimension of r cubed, which is 3. So the dimension of the image of TA is then 2. And that's helpful in our calculation of the image. Once we know what the dimension of the image is, that makes it slightly easier to actually calculate a basis, for example, of the image. On this slide, we're now going to do a general result about the image of a linear transformation of the form T subscript A for some matrix A. And what we will show is that the image of such a linear transformation is equal to the column space of the matrix A. You will remember that the column space was defined a couple of lectures ago as the subspace spanned by the columns of A. Why is this true? Let us think about a little bit about matrix multiplication. Another thing I will need is the standard basis vectors, which we met already. So we will write, as usual, EI for the ith standard basis vector. So that is the column vector which is 0 everywhere except for a 1 in position I. I claim that if you matrix multiply a matrix A into EI, is equal to the ith column of the matrix A. We'll see why this is useful in a moment, but we're going to prove it now. This is just a few easy observations about matrix multiplication. So let's give the columns of A some names. We're going to call them C1 up to Cn. So this is my matrix A. I'm just giving names to the columns. I'm calling them C1 up to Cn. But A is equal to A times the identity matrix. And I can rewrite the identity matrix as the matrix whose columns are E1 up to En. And you will also remember that matrix multiplication works column-wise. So when you multiply a matrix A into a matrix whose columns are E1 up to En, the result is the matrix whose first column is A times E1 and whose second column is A times E2 up to A times En. Okay, so on the left of this chain of equalities, I've got the matrix whose columns are C1 up to Cn. On the right, I've got the matrix whose columns are AE1 up to AEn. So, from that, AEI is equal to the ith column of A, which we called Ci. You proved a special case of this in one of the questions on your midterm problem sheet. And you could, if you chose, prove the general case which we've just done the same way. Now we're going to use this to prove the result which we were talking about at the start of this slide, that the image of TA is equal to the column space of A, in other words, the span of the columns of A. So since we gave those columns names, this column space is the span of C1 up to Cn. Let's take an element in the image of TA. Well, something in the image of TA looks like a vector multiplied by A. We're going to give names to the entries of x. x1 up to xn. And now a times x is equal to a times x1 times the first standard basis vector plus x2 times the second standard basis vector, and so on up to xn times the last standard basis vector. That's because if you add up that linear combination of the standard basis vectors, you just get first entry x1, next entry x2, and so on. Okay, matrix multiplication has the linearity property, so we can rewrite this as x1 times a of e1 plus x2 times a of e2 all the way up to xn times a times en. But we've just seen that a times the ith standard basis vector is equal to the ith column of a. So this is x1 times the first column of a plus x2 times the second column of a all the way up to xn times the last column of a. Right, what is that? That is a linear combination of the columns of a. It's a linear combination of c1 up to cn. So it's an element of the span of c1 up to cn. We have proved that every element of the image is also an element of the span of the columns. Now we have to prove that every element of the span of the columns is an element of the image. But we can do that in exactly the same method, just reading these equalities backwards. A typical element of the span of the columns would look like a1 times c1 plus a2 times c2 up to an times cn, where the a's are some scalars, some elements of the field from which the entries of a come. So we're really just going to write all of the equalities that we had here backwards. We start off with a times c1 up to an times cn. We notice that that's equal to a1 times ae1 plus a2 times ae2 up to an times aen. We then use the linearity property of matrix multiplication to write this as a multiplied into a1 e1 plus a2 e2 all the way up to an en, which is a multiplied into the vector whose first entry is a1, next entry is a2 all the way down to an. And that, of course, is TA applied to something. That's TA of the vector a1 down to an. So this, as it's TA applied to something, it is in the image of TA. We've now proved that every element of the column space is an element of the image of TA, and therefore the image of TA equals the column space. Fine, so we now have the general result that if you have any linear map of the form T subscript A, so any linear map between column spaces given by left multiplication by a matrix, then the image of that linear map is simply the span of the columns of the matrix. Let's return to our example in which A was the matrix 1, 2, 3, 4, 5, 6, 7, 8, 9. We computed the kernel of the linear map TA from R cubed to R cubed, and we found that it was one-dimensional and it was spanned by the vector 1, minus 2, 1. We then applied the rank nullity theorem to learn that the dimension of the image of TA is 2. We also know from my last slide that the image of TA is equal to the span of the columns of A. 1, 4, 7, 2, 5, 8, 3, 6, 9. So those columns are not a basis of the image of TA, because the dimension of the image of TA is 2, so a basis must have size 2. So let's say we want to complete our study of linear map TA by finding a basis for the image. Well, there are many possibilities. Let's just look for one basis. Well, we know that the dimension of the image is 2. So if we can find 2 linearly independent elements inside the image of TA, then their span is a subspace of the image of dimension 2, so it must be all of the image. So if we find 2 linearly independent elements in the image, then they're a basis for the image. So if you just take the 2 columns, well, you can check directly that the first 2 columns, 1, 4, 7 and 2, 5, 8, are linearly independent. That means they're a basis for the image of TA. They're certainly linearly independent. You can check this just by solving the linear equations, or by the methods you already learned for determining whether 2 vectors are linearly independent. That means the dimension of their span is 2. So their span is a subspace of the image of TA with dimension 2. But the dimension of the image of TA is 2. So their span is in fact all of the image of TA, because if you have a subspace U of a vector space V, and the dimension of U equals the dimension of V, then U equals V. We proved this in one of our subspace lectures. So those 2 vectors are linearly independent, and they're a spanning set for the image, which means they're a basis for the image. Alternatively, you know from our last lecture how to find a basis for the span of a collection of column vectors. You will remember that we had a method for finding a basis for the span of some column vectors, which was to put those column vectors as rows of a matrix and then find the row-reduced echelon form of that matrix, and then the non-zero rows, once they were turned back into column vectors, would be a basis for the span. So that will be an alternative method for finding a basis for the vector space spanned by the columns of our matrix.